The purpose of this video is to show you how to calculate current and voltage in a complex combination circuit. In the previous video, we simplified a very complex combination circuit down to a single resistor value, which we call the equivalent resistance, or which is the total resistance of the circuit. What we'll do in this video is start from that point and work our way out until we get all the values for current and voltage for the entire circuit. Now that for this circuit in particular, where we have 9 resistors, it's quite a task. But if you can follow along and understand what we're doing at each step and how to solve using Ohm's law, you'll have no problem solving for the more simpler circuits. In this video, we are going to use Ohm's law throughout the circuit to find current and voltage. There is another method for calculating those values, and that would be the current and voltage laws of proportionality as applied to series and parallel circuits. But that's for a later video. Right now we're all familiar with Ohm's law, and so we'll just use that to find all the values. And also in this video we want to solve for all the values for current and voltage throughout the circuit. So Ohm's law is definitely the way we want to go for this one. So let's go ahead and begin. We'll go ahead and find the total current in the circuit by using our total values here. We'll go ahead and write the Ohm's law up here, which we're solving for current, so we'll go ahead and write IT equals E over R, and so we have a total source voltage of 200 volts and a resistance of 46.64 ohms. So we'll go ahead and bring up our handy dandy calculator and punch these values in. We get a grand total of 4.288 amps. Okay, that's our total current. Now, if you recall, in a parallel circuit, the current will split at each junction or at each branch. In this circuit here, this 4.288 amps is going to be the total combined current of the current flowing in each of these two branches. So if you recall, one of the rules for parallel circuits is that the total current equals the sum of the branches, or the sum of the currents in each of the branches. Once we calculate the current in each branch, we should be able to add those two together and get the 4.288 amps for a total. So let's go ahead and let's look at this circuit here, and what's going to be the voltage across each of the two branches? Yeah, it's going to be, we have a simple parallel circuit here, so we know that each of these is going to be 200 volts. So we'll go ahead and just write that in right here, 200 volts. And we will be filling out a peer chart for this, because if we just have the values just scattered around all over the place, it'd be really difficult to keep track of all of our calculations. So a nice peer chart set up with all the values, all of the resistors, will help us keep everything in order. So let's go ahead and use Ohm's law here and calculate the current through each of these two branches. So we have I123 is going to be equal to 200 divided by the 79.67. So we'll bring up our calculator once again. Okay, 2.51 amps. There's I123, so 2.51 through this branch. And now this branch here it should be the difference between the total and this here, but we'll go ahead and use Ohm's law to calculate this as well. I4, we'll just call this I4 through 9. 200 divided by the 112.47 ohms. So we'll go ahead and punch that into our calculator. We get 1.77. Check that. 1.7. Let's go 1.778 on this one. Okay, so let's go at least 3 digits when we're doing our current. Let's go out at least 3 digits past the decimal point for our values. Okay, so we have the current through each of these 2 branches. If you look at that, if you add those 2 together, yeah, it does equal the 4.288 amps. So we're right on task there. Those are correct. Okay, so how does that help us? Well, we know that in a series circuit, current's constant in the circuit. So if we look at this first branch here, we treat these 2 resistors, since they're in series, we use the rules of a series circuit. So we treat this like a series circuit. So we'll just use Ohm's law to calculate the voltage drop across each of these 2. Looking at it as a parallel circuit, we know that there's 200 volts across each of these 2 branches. 200 volts across this branch, 200 volts across this branch. However, there's 2 resistors in this branch. So there's not 200 across both resistors, or each resistor. There's 200 volts across the entire branch. So they're going to share that voltage. So it'll be dropped proportional to the resistance. So we'll go ahead and use the Ohm's law to calculate current through those. So we have I1 and 2 is going to be equal, actually, we're looking for an E here, so let's write E1 and 2. Okay, I times R, so what did we say I was? 2.51 for this branch, times the resistance of 16.67. So we'll go ahead and plug that one in. $41.84. Volts. Now for the R3, it's going to be 2.51 amps times 63 ohms. Okay, so E3 equals 158.13 volts, and the sum of those 2 equals 200 volts. So we see that we are correct with those calculations. And of course, this resistor here, R4 through 9, will have 200 volts across it, and we can go ahead and calculate the current through that path as well. R4, let's write this as, since we're going to go ahead and calculate the current. Well, we just calculated the current down here in the previous step. So we'll scroll down here, and we have 1.778 amps for that branch. So let's go ahead and write that in up here. 1.778 in this branch. Okay, and we know that there's a total of 200 volts since this is a single resistor here. Okay, let's look at what we got. We calculated the voltage across resistor R1 and 2 to be 41.84 volts. Now, why is that significant? Well, we know the rule for voltage in a parallel circuit. Two resistors in parallel will share the same voltage. They'll have the same voltage dropped across them. So that's what we have here. R1 and 2 are in parallel. So we can go ahead and plug in that's 41.84 volts across each of these two resistors. Okay, and use their resistor values along with the voltage to calculate the current through each one. We can't use the current for this branch because it splits. Yeah, that the current in this branch, the total current in this branch does go through R3, and then it splits, and it's going to be shared proportionally amongst resistors 1 and 2. So we'll go ahead and calculate the current through those two resistors. So I1 is going to be equal to 41.84 divided by 25. And we'll go ahead and set it up for the next one as well. I2 equals 41.84 divided by 50. So we'll go ahead and plug those two into our calculator here. 41.84 divided by 25 is going to give us 1.67 amps. 1.67. Let's go out. Let's go out all the way. 3.6. We want to go at least 3 decimal places, maybe even 4 on these current values. And for I2, we plug that into our calculator, and so we have the 41.84 divided by the 50. And what should we expect here? A higher or lower value than through I1? Well, the resistance value here is twice as much, so we should expect to see half as much current going through. So we have point. You know, I'm still getting used to this calculator disappearing every time I go to write after I calculate the value here. So it'd be nice if this thing would just stay up until I minimize it. 0.8368 amps. Okay, so there's our two current values through those two resistors. And we go ahead and plug that right into our pure chart as well. We have a pure chart set up for this, and we have to keep track of all the values. I'll go ahead and pop up that pure chart. We got it right here, and we just calculated the currents through R1 and 2, and we got them right here. 1.67 amps through R1 and the 0.8368 through R2, and we had basically 2.5, 2.51 through R3. So those are put into our pure chart. Okay, so we'll go ahead and continue from this point. We have this complete now. This is done, this first branch. So everything else is going to be from here on out. Resistors 4 through 9 are what we have to calculate. And so we have the overall resistance, and for this equivalent resistance here, we have that resistance value. But what's going to be the voltage in this branch? Well, there's no resistors in series with this branch here. So far it's just one parallel branch ahead of it. So since we see no resistors in series, this is going to get the full 200 volts across this branch. Okay, so this is our starting point here. 200 volts, 112.47 ohms. We can go ahead and calculate, well, we should go ahead and calculate the current through this. Or actually, we have the current through this branch. We need to go to the next step and expand the circuit, expand this branch here to what it was, remove R8 as a separate resistor here, but we know the current through this entire branch. So it was 1.778 amps. So we'll go ahead and put that right here. Yeah, there's our current. And we're going to treat this as a series circuit. We have two resistors in series here. So we know that this resistor equivalency and this resistor here will have that full 1.778 amps going through them. So we go ahead and calculate the voltage dropped across each one of those. We know that the sum of these two voltage drops will equal to 200 volts, but it's going to be shared proportionally to the resistance of each. So we'll go ahead and set this one up. E8 is going to be equal I times R, so we have 1.778 amps times the 50 ohms. So we'll plug that one in to our calculator. Okay, 88.9. So 88.9 volts. Okay, so if we subtract the 88.9 from the 200, we should be expecting about 111 volts across this, but we're going to go ahead and use Ohm's law to verify that. Just as a way of double checking to make sure we haven't made any mistakes. So we'll do E4 through 9 will be equal to I times R. So we have the same I, 1.778 amps, times the resistance value of 62.47 ohms. We'll punch that into our calculator. Look at there, 111.07. volts across this resistor combination here. So we have an individual resistor value here, and we just calculated the voltage drop across it. So we go ahead and put that into our pure chart since we have it here. 88.9 volts across R8. So we have R8 over here. The voltage was 88.9. Okay, 88.9 volts across that one. So we'll go back to our circuit and plug in the other voltage calculations that we have already made for the previous resistors. R1 and 2 we had 41.84 volts. So we'll put 41.84 here for these two. Okay. And for R3 we had that calculation as well. E3 was 158.13. Okay. So we're at this point where we have to expand this equivalent resistance here of R4, 5, 6, 7, and 9. And since this resistor equivalency has 111.07 volts, every branch past this is going to have that voltage as long as it's parallel. So we'll scroll up to our next circuit and we'll fill in the 111.07 volts. So that's what we're working with. So R9 has 77 ohms and 111.07 volts. So we can go ahead and calculate the current through R9. The 111.07 divided by 77. .442 amps through R9. So we can put that into our pure chart. 1.442 amps for R9. There we go. Okay. Alright, so we have this equivalent resistance here of R4, 5, 6, and 7 left, and looks like we're headed down the home stretch here. We'll go ahead and expand this branch out. Just scrolling up here. So we know that R4, 5, and 6, 7 are in series, and so it's going to have a constant voltage, or excuse me, constant current of the 1.442 amps through it. So we'll go ahead and apply this amperage to each of these resistances and get the voltage drops across each. And the sum of these voltage drops should equal 111.07 volts. So E equals I times R. Okay, E4 is going to be 1.442 times 85. Punch that in. Okay, well, we'll leave that there. So there's our current times 85. 122.6. 122.6 volts for E4. E5, same current, of course, 1.442 times the 200 ohms. Okay, we'll go ahead and punch that into our calculator. .4. Does anyone see what we just did here? I brought up I9, the current through resistor 9 here for our current value. That's clearly not the case. 1.442 amps is the current through I9. Now, these two branches are sharing the same voltage, but definitely not the same current. If we scroll down here and look at this resistance value here, R4, 5, 6, 7. We go down here. Actually, R4, 5, 6, 7 is right here. We have 200 ohms, 85 ohms, and 45.95 ohms. We need to go ahead and write down that resistance value right here and calculate the current through this branch. So we'll go ahead and bring up our calculator. That resistance value got lost in the process of rearranging these circuits for this video here. 85 plus the 200, that's obviously 285, plus the 45.95, and that's 330.95. There's our resistance value for this. So 330.95 is what we have for the resistance of this branch. we have to use Ohm's law here, calculate the current through this branch, and then apply it to each of these resistors. So that'll give us the correct values. So I4 through 9 is going to be 111.07 divided by this resistance value of 330.95. We'll plug that in to our calculator. Okay, here's our current through that branch. 0.33, and I promise you, one day I'll get used to this thing disappearing as I start to write. 56 amps. Okay, so that's the number we're going to use for our calculation that we just did a minute ago. 0.3356. So we'll take this out of here. And this, let's just get rid of this. Okay, we'll get it right. 0.3356 times each of these resistance values, and it'll give us the voltage drop across each of these resistors. So R4 would be 85 ohms. We can go ahead and write it for this one too. 0.3356 times 200, and then E67 will be 0.3356 times 45.95. Now we'll punch in each of these into our calculator. 0.3356 times 85. Okay, there, that looks good. 28.53 volts. Okay, now for number 5, resistor number 5, we'll punch that in. 0.3356 times the 200 ohms. Okay, looks much better. 67.12 volts. And then finally, for this resistor equivalency of E6 and 7, we'll punch that one in. And it has 15.42 volts across that resistor. Well, we'll go ahead and bring these up onto our peer chart. 15.42, well, that's for this resistor pair. So 67.12 and 28.53, and then the current through these resistors as well. So let's go ahead and bring this one up right here. So we had 4 and 5. The voltages across 4 and 5, we had 28. Keep consistent colors. 28.62 volts for 4, and number 5 had 67.34 volts, and then we have the R6-7 combination. The current through R4-5 was 0.3367. Okay, now we have to do R6 and 7. And look at what are we missing here? The voltage across R9 we never filled in. That was the 111 volts. So we'll go ahead and put that in there. Okay. As you see here, we're going to be wrapping this up real soon, coming down the home stretch on this one. R8 we're missing the current through R8, and that was the one 1.778 amps. Okay, we'll switch back to our circuit here. Go on to our next circuit, our final circuit, and what we have to be aware of is that R6 and 7 has 14 or 15.42 volts across it. So we're going to have to apply that to those two resistors right here. 15.42 volts. Going across each of them because they're in parallel with each other. So we definitely have to apply our rule here for parallel circuits, for voltage in parallel circuits, and use Ohm's law. We're going to write I equals E over R, so I6 is going to be the 15.42 volts over the 100 ohms, and that's going to be 0.1542 amps. And then for I7 we'll get that voltage, 15.42 volts, and divide it by its resistance of 85 ohms. We'll plug this one into our calculator. Okay, 0.1814. .1814 amps. Alright, so there's our current through those two resistors, and that should about wrap it up. We'll go ahead and bring these over to our pure chart, and we'll bring the voltage over as well, where we have 15.42. And there I go again, 15.42 volts across each of these two. Okay, we'll go to our current and put those in, and let's make sure we get that accurate. We had 0.1542 amps for R6, and for R7 we have 0.1814 amps. Okay, there we have it. There we've calculated all the voltages, or all the values of voltage and current for all the resistors in our circuit here. And as you can see, we didn't calculate any of the values for power, but you can simply use Watt's law here and do I times R to get the power across, or power that's being consumed or dissipated by every one of these resistors in the circuit. So that was quite a circuit. We have 9 resistors. We've used the rules for series and parallel circuits, applied Ohm's law to those resistors, and we've done it. We've calculated everything we set out to calculate. For this series parallel circuit, if you can do this one, once you've seen how to do it and work through it, if you can do this, you should have no problem with any of the other circuits that you'll be seeing here in this section. So just please use this to help you get through any problems that you're having trouble with, and if you have any questions, just leave a comment and I'll definitely get back to it. Enjoy.